My name is Colin Mooney, and may I just say, you looking fine today. Anyway, you can tell by our formal attire that we mean business. Also, that we're upper middle class. Today, my associate and I are here on behalf of the Derek Zoolander School for Children Who Can't Read Good and want to learn to do other things good too. And we'll be teaching underprivileged high school graduate Tristan Kindig, a.k.a. PK Money, how to do calculus.
What's up, Gando? Underprivileged kids represent.
You may recognize us from similar films such as Tristan Learns to Count, Tristan Learns to Read, and my personal favorite, The Chain Rule. You can look, but you can't touch. Good one. Anyway,
get the first lecture going.
Hey, no eating or drinking in my classroom.
Okay.
This is the class for intro calculus. So, Tristan, let's see what you brought to the table.
So I was thinking about some of the stuff you told me in our very first meeting, and I made a joke. I made a math joke, right?
Right.
So I took the integral of 1 over cabin d cabin. Right. I was using cabin as our variable, right, of integration here. It's like 1 over u du.
Yeah.
And I said that the integral of that, the indefinite integral, so I turned the c later, is ln absolute log cabin plus c, right? Right? Is that? I think it's right. And I thought it was really funny. I thought it was a good joke. I thought it was a good math joke. And I'm wondering what you think.
I think that's absolutely ridiculous.
But it fits with the real world, right? It's a log. It's a natural log cabin, like the thing that like lumberjacks and Canadians live in. Like that's why it's supposed to be funny.
That's insensitive and absurd. I don't see how you possibly could think that this would be okay in my class.
I'm just trying to please you.
You're so stupid.
I know, you told me that a lot.
Oh my gosh, this is ridiculous. Okay, good thing we're prepared for students like you, those that belong in the classroom upstairs.
I'll keep trying, Professor Gold.
No, come on. We're going to have to resort to these measures. Come on. Alright, so this here is our Scooby-Doo calculus presentation for them underprivileged children.
Alright, so here's what's going on today, alright? So, it's Scooby-Doo mystery, right? We're at the town of Integralville, and there's a pie factory there that's being terrorized by the derivative monster. So the derivative monster has been running through the factory for a little while, and you can derivatize all the pie there until 0. And then recently, he messed up the water tower there. So, now Scooby and the gang are on the case. Got to take care of things. Alright, so first, of course, they got to go meet up with just the manager and get permission to scoop around. So they go and see the manager, who's seen K as we see. Thanks for that profile picture, by the way. Alright, and they got to go check out the water tower. So let's take a look at our first example then. Alright, so Scooby and the gang show up at the water tower, and we see that the water tower is cone-shaped for decorative purposes, of course, and it has a radius of 12 feet, a height of 24, and we know that when the water level is at 4 feet, the water level changes at a rate of negative 5,400 divided by pi feet per hour. Right, so since the tower shows signs being tampered with, the gang's interested in how long the water tower took to drain so they can see which maintenance man was on the job at the time. So they're interested in knowing how fast the water drains from the cone, the total volume, and the amount of time it takes to drain completely. Hey Tristan, you got that all down?
Yeah, we're good.
Alright. So, let's get at it then.
Alright, so Tristan, let's see how you do this. So from the diagram, we're given that dHdP is negative 5,400 over pi feet per hour, and the height of the water is?
Is that 8?
No, it's actually not 8.
Sorry, I'm really sorry, Dr. Galappsdflslfjioejils. It's just that normally when I get a problem wrong, you know how you beat me above the head?
Yeah, definitely.
And it's kind of, like my vision's been deteriorating.
Alright, take another look.
I'm really sorry.
Take another look.
Okay, I'll get closer this time. And then
take another look.
I think, I see it now. It's 4 feet.
That's correct. Now our radius is 12 feet and our height is 24 feet. So we want to make it so that we have only one variable. And the variable that we will be using is, as you can see down here, h. So we have r over h is equal to 12 over 24. So our radius is h over 2. So this is the volume equation right here. And once we plug in our new r, okay, And from this, we can manipulate this equation to get this. Then we find the derivative of it. And the dv dt is pi times 3h squared over 12 of times dh dt. Now, when we plug in our variables, we have 4 over here and negative 5,400 over pi here. And the pi's cross out, and we do a lot of good stuff on our calculator. And, as Mr. Walter Georges would say, keep the calculator for this one. And we have the rate of change of the volume as negative 21,600 feet per hour, but just for purposes, we'll put it in seconds. So we divide by 3,600 seconds, and we get negative 6 feet per second. Now, part B was to find the volume. The volume, just using the standard volume equation up here, is 3,619.115 feet cubed. That's our volume. Now, to find the amount of time it will take to drain completely for the water, we find our volume, or we take our volume and we divide it by the rate. And we get 603.186 seconds, which is just a little bit over 10 minutes. Thank you. Okay, so the water from the water tower is pouring into the control room of the pie factory. Bad news though. It's bring your child to work day, and what child doesn't want to be in the control room? Obviously. So, unfortunately, we're stuck with 12 adults and 31 kids in a space that is 12 by 30 by 12 feet. This is all fine and dandy, but they'll all die once the water reaches a height of 8 feet. So, do me the favor of finding out how much time they have to live. Unfortunately, it doesn't matter because only one kid survives. And this kid gets haunted by all the dead spirits and stuff of the other people. So, what we're looking for is an optimization problem to see how to maximize his life by seeing the number of kids that died, which would and therefore increase his life. Alright, so unfortunately, none of your work matters because only one kid survived. So, from this, we can find that his life is actually dying, getting shorter because of all the ghosts and stuff from the dead people coming and haunting him, etc., etc. Very, very sad. So, we want to find the maximum lifespan that he could possibly have in relation to the number of dead children.
The volume of the factory is given by the equation 12 times 30 times 12 using the width, length, and height respectively. We get that the total volume is 4,320 feet cubed, but we're only interested in the height of 8 feet, so instead we do 12 times 30 times 8 and find that the total volume of that is 2,880 feet cubed. By dividing this value by the rate at which water enters the factory, 6 cubic feet per second, we find that there are 480 seconds, or 8 minutes, before the factory is built. Okay, for the ghost problem, we use the equation given to us, y equals 5 times 3x minus 5.9 squared minus 3x plus 8. In order to optimize, we must derive this function and get y is equal to 30 times 3x minus 5.9 minus 3. In solving for x, we find that x is equal to 2, and the optimization for this problem would be 20 children must die for the boy to live the longest. To prove this, we use the first derivative test, and checking on the interval from 0 to 2 and plugging into the first derivative, we find that from 0 to 2, the quantities are negative, and on the interval from 2 to 3, the quantities are positive. This sign change shows us that what we have found is a minimum, and we have in fact optimized. Alright, you ready for the next one, Champ?
Yes, I am, Pop.
Alright, so, all of a sudden, the derivative monster just pops out of the woods, and waving his arms, he causes the whole group to disperse. So, the chase scene, as usual, automatically goes. Okay, so, Shaggy's fleeing, and the monster's following him.
Oh my goodness, I hope he doesn't catch him.
Yeah, that's right. Alright, and the two pass under a street lamp. So Shaggy, of course, immediately evaluates, hey, we're both running at 10 feet per second, we're 10 feet apart right now, the street lamp is 12 feet tall, the monster is 7 feet tall, and Shaggy is 12 feet from the street lamp.
Wow, Shaggy's a real nerd, Pop. I would be a lot more concerned about running away.
So he's wondering now, at what rate is the monster's shadow growing at that very instant, because the shadow is cast by this lamp upon him, and when will that shadow reach him? You ready to try to figure it out?
Yes, I am.
Let's do it. Alright, so right here I've got another picture of what we had up there. So we know that this is your monster, who is 2 feet away from the light, which is 12 feet tall, and the monster stands at 7 feet. And Shaggy is 10 feet away from the monster, and we have X is the distance from the light to the monster, which is increasing, and Y is the shadow that is cast by the light on the monster, which is also increasing. So it's important to recognize that we have two right triangles going on over here, and that means that we've got like triangles. They're similar. So we can set it up as 7 over y, the height of this triangle over the length of this triangle, is equal to 12 over x plus y. From this point of comparison, all we have to do is multiply out the denominators, and we'll get 7x plus 7y is equal to 12y. Then we can subtract 7y, and we get 7x is equal to 5y. Now, because we're looking for a rate of change, what we need to do at this point is derive both sides. So we get that 7 times dx dt is equal to 5 times dy dt. So we don't have a value for dy dt, that's what we're looking for, and we do have one for dx dt because we're told before that both move at a rate of 10 feet per second. So we're going to go ahead and sub in 10 for dx dt, and we'll do 7 times 10 is equal to 5 times dy dt, and we get 70 is equal to 5 dy dt. Then by dividing 5 from both sides, we find that dy dt is equal to 14 feet per second. So we know the shadow increases at a rate of 14 feet per second. Alright, for the second part, Shaggy is interested in when the shadow cast by the monster will reach him. So essentially we want to know when the shadow's length will be 10 feet, because that's the distance between the two. So the way we can do that is by deriving the rate we got before to find a length function. So the integral of 14 dx will get us that a length function is 14x. Right now we're going to go ahead and disregard the plus c because it's easier to take account for it later on. Alright, so we know that we want 14x, the length function, to be equal to a length of 10 feet between them. So we divide both sides by 14, and we're going to get that x is equal to 5/7. Now is where we're kind of going to take account for a plus c, because it's important to keep in mind that when we first started, the monster was already 2 feet away from the light, and his shadow is actually first cast the second he moves away from being directly beneath it. So we know that 2 feet have passed, which by referring to our rate of 10 feet per second, we can find that in the 2 feet that have gone, that he's already moved, it means that a fifth of a second has already gone by. So we take our x equals 5/7, have to subtract 1/5, so we get a like denominator, so that's going to be 25 over 35 minus 7 over 35 to get us 18 over 35. So the shadow will reach Shaggy in 18/35.
The monster didn't catch them, did he?
Oh, no. Shaggy got away.
Did he do a cost-benefit analysis and realize it just really wasn't worth it?
Yeah, that's pretty much what happened.
I guessed as much.
So afterwards, of course, the group got back together, and they talked about all the evidence they found. They had seen that since the water tower took 10 minutes total to drain, it must have been Old Man Jenkins, who was on the job to begin with. He must have done it.
Oh, Old Man Jenkins.
So they looked him up and went over to his house, but when they got there, guess what?
What?
He was dead. Ah! Watch, see what happens next.
So, here's what happens next. Leaving the murder scene, Scooby spots a derivative monster in a van parked across the street. The van immediately speeds up, and the gang hurries away in the mystery machine to go get him. Yep. Fred takes a shortcut, which he knows will get them at an intersection where there are two routes, because it's an intersection that's perpendicular. Okay, So the mystery machine is 2.2 kilometers from the intersection.
I
And
think
the
that's
van-
actually a point two.
Yeah. I said 0.2.
Okay.
And then the van is 0.5 kilometers from the intersection.
Got that one right. Keep going, man.
Yeah. The mystery machine travels at 44 kilometers per hour. The van travels at, wow, 110 kilometers per hour. Wow. Velma wants to know A, the distance between the cars. B, the rate at which the distance is changing. And C, the mystery machine passes a stationary tree 5 meters from the road. If the distance between the machine, at what rate is the distance growing between the two 1 second after the mystery machine passes? Alright, so here we have another diagram I've sketched up of the information we know. We know that the mystery machine is coming this way at a rate of 44 kilometers per hour, and the monster machine is coming this way at a rate of 110 kilometers per hour. They're going at perpendicular roads, so it makes a right angle. We know that the mystery machine's road is 0.2 kilometers, it's a shortcut, and the monster's is 0.5 kilometers. I've labeled A, B, and C because we're going to need to be using the Pythagorean theorem to find the distance between the two cars, which we're looking for. So, simply A squared plus B squared equals C squared. Sub in our values, we find C is equal to 0.539 kilometers, and that's the distance between them. Okay, to find the rate at which the distance between them is changing, however, we need to make it a related rate situation. So we take our same Pythagorean theorem, and we're going to simply derive. So implicitly, we find that 2a times dA over dt plus 2b times dB over dt is equal to 2c dc dt. We have everything except for dc dt, which we're looking for, so we simply plug in 0.2 for a, 44 is the rate that the mystery machine's moving, 0.5 for kilometers for b, and 110 kilometers per hour is the rate that the monster is moving. And 0.539 is the distance for c. By putting it all together, we just use algebra and then find that dc over dt is going to be equal to 118.367 kilometers per hour. Alright, lastly, we're looking for the rate of change from a tree on the side of the road to the mystery machine. We're told that the mystery machine is 5 meters away from the tree before, and then after 1 second, we're looking for the rate of change. So we also need to put in that the mystery machine was moving at 44 kilometers per hour, so we can simplify to 45,000 meters, we've got on the same term. 44,000 meters, so we've got on the same term. And we change hours to seconds, which involves having 3,600 seconds, so we divide and get 12.22 meters per second, so it's moved 12.22 meters in that time. We're going to use Pythagorean theorem again to get this side, and we find that the side between the mystery machine and where the tree was before is 13.203 meters. And then once again we do rate. The only difference this time is we need to keep account that the rate between the tree and where the mystery machine originally was is 0, so that part's going to get rid of itself right here. 2 times 5 times 0. It goes away. Ultimately, the rate of change between the tree and the mystery machine is going to be 40,724.08 meters per hour. Upon capturing the derivative monster, which is great feat for the mystery team, they see that they have the derivative monster, and of course they want to figure out who it is. So, they rip the head off, or the fake head off of the derivative monster.
So it wasn't his real head?
No.
They didn't just like decapitate him accidentally?
No, they didn't decapitate him.
Okay, that'd be really gross.
They did because the head was on very, very tight.
Oh, I hate that.
Yeah, I know. It's so annoying.
Alright.
But they took the fake head off, and it was revealed that the real culprit was, now this is a very, very interesting thing, Christine K., the
Really?
manager of the Pie Factory.
Of the Pie Factory?
Yeah.
Huh.
Who would have thunk? So,
Not proper grammar.
in order to keep him restrained, they tie him on a leash to a pole, which then turns into a somewhat predicament for Hustine because, of course, he wants to escape. So in his escaping, he essentially turns the pole and rope into a spring mass system.
Huh.
So, let's come to the paper to see how it all works. So Hooke is tethered to a pole by a leash made of rope. We find that his mass is 65 kilograms, and the spring constant of the rope, which is basically the stretchiness of the rope, is 400 Newton meters. We also find that from the pole, the max distance from any point is 5 meters. So we find the potential energy of the spring at the max position from the pole. And we find that that is equal to 1/2 kx squared. Once you plug in your spring constant and 5 for x, we find that the potential energy of the spring is 5,000 joules. With this, the reason I have it equal to the kinetic energy is because the breaking, once Hooke breaks the rope and continues onward, the potential energy he had from the spring will become his kinetic energy leaving the spring. So we have the 5,000 come here, and we plug in his mass here, and we solve for his velocity, and we get 12.4 meters. Okay, so I'm going to explain work and its application in calculus. Work is the integral of force. Normally, when you see a work in physics, you would see work is equal to force times distance. The integral sign is just something that you can use to find the Riemann sum approximation of the work. In work, a work graph is a force times distance graph. The reason why it's the integral of just force is because force is this, and your distance or displacement are these ones. As we know, the Riemann sum is the approximation based on making rectangles underneath and trying to get as close to the actual value as possible. The integral sign just makes the gaps between the displacement so small that we can assume that the rectangles get you as close to the actual value as possible. So Hooke starts at one end of the rope and pole system at -5, and he runs all the way to the other end, which is 5. And from this, we have our force being k times x, and we already have k. So once we do a little bit of manipulation here, we evaluate it here after we integrate, and we get our work to be 10 times the distance. Our next unused term happens to be the velocity. This part right here has to be a maximum, and as I said earlier, the maximum velocity is the only velocity, which is 12.4 meters per second. Through this, we can take our calculation, and upon realizing that he broke away, it took us 60 seconds to do this equation. So if f of 60 must be less than or equal to f of 0 plus this area, which is our Lagrange of our maximum, 12.4 meters per second, times x minus c, which was 60 minus 0 over 1 factorial. F of 0 is 0 at 0. So after 60 seconds, Hooke must have traveled less than or equal to 744 meters. This means that after finding the area, this area is the total possible area that he could possibly be in.
So, with this knowledge, the gang are once again able to capture Justine, and they'll stop the plot just as always. Darn meddling kids.